Welcome. Our topic is artificial intelligence in self-driving cars. My name is Dharavath Sanjay Bhargav and my teammates are Kowshik and Aman. We have divided our report into 10 parts that are introduction, why self-driving cars, history of autonomous vehicles, ecosystem, workflow of autonomous cars, perception, planning, cybersecurity, data privacy, then conclusion. Let us start with introduction. Self-driving cars are also known as autonomous vehicles is a car incorporated with vehicular automation which enables the car to operate itself without the need for the human at the steering. Through its ability to sense the environment, recently significant improvements have been reported in the development of vehicular sensors for performing different simple and complex tasks including object detection, localization, tracking and activity recognition for numerous applications. Why self-driving cars? Self-driving cars can be a source of life-saving technology. Firstly, the goal is to remove the possibility for human errors on the roads and improve safety. Roughly about 1.3 million people die in car accidents around the world each year. 90% of the car accidents are caused by human errors. Self-driving cars will eliminate the key source of human errors as they will not make any error of judgments. And self-driving cars are greater mobility options, especially for elderly and disabled users. And they are eco-friendly, a great drop in emission than convection cars. And they reduce traffic conjunctions. Now let us see a history of the self-driving cars. At initially in 1948, they have introduced a cruise control. Cruise control is like uh, fixing of a speed. And then in 1999, Ohio State University launched the Autonomous Vehicle Project. It is the start where autonomous like self-driving cars have been born. And as we can see in timeline 2004, 2009 and 2012. It is the Google where the self-driving car project has been initiated. Google's autonomous car passes a 14-mile driving test in Nevada. And then in 2013, Mercedes and Infiniti produced cars with radar sensor and some autonomous driving features. Then in 2015, Tesla releases its autopilot self-driving mode. Many popular automotive companies like Ford, Uber started to work on self-driving cars. Major acquisitions and partnerships and cruise automation are from Toyota and Jaybridge Robotics, Uber and Volvo. 29 US states have passed a law of permitting autonomous cars. Ecosystem. The physical ecosystem of autonomous vehicle consists of so many parts like GPS tracking, light detection and ranking, cameras, ultrasonic sensors, central computers, radar sensors, and so on. Yeah, in the next slide we will discuss about this. Cameras provide a real-time obstacle detection to facilitate lane departure and track roadway informations. Like we can say that from the cameras, the algorithm takes photos, and from the photos it will detect the roads, lanes, pedestrians, traffic signals, vehicles, obstacles, etc. And radars are radio waves detect short and long range depth. Like they detect any object which incoming to the vehicle. LiDAR. It measures the distance by illuminating target with pulsed laser light and measuring reflected pulses with sensors to create 3D map area. GPS. Global Positioning System. Triangulates position of car using satellites. Ultrasonic sensor uses high frequency sound waves and bounce back to calculate the distances. Ultrasonic sensors are best if they are in close range. Central computer, like it's a brain of the vehicle. All the algorithm of the self-driving cars will be in the central computing. DSRC based receivers. It communicates device permitting vehicle to communicate with other vehicles using DSRC, a wireless communication standard that enables reliable data transmission in active safety applications. Now let us see the workflow of autonomous driving. As we can see, working of autonomous cars, sensor input, perception, planning, control and actuation. Like the sensor inputs the data into the perception, the data will be analyzed and there will be output, and planning checks it, and then if the planning is correct, then it will control the vehicle. Thank you. From here Kowshik will continue.
Thank you, Sanjay. My name is Kowshik Vinay Kumar. Now I am going to discuss the about one of the crucial process in working of autonomous cars, that is perception. Now let us see about the perception process. Perception process is responsible for understanding the world around the vehicle. This is done by extracting the relevant information and required knowledge about the environment using sensors like LiDAR and RGB depth cameras. It is always considered as the initial stage of computational pipeline for self-driving cars. This process is very critical for proceeding to the planning process. Perception includes numerous critical tasks like detecting the road and lane, and also detecting the other vehicles and obstacles in order to drive safely, and also traffic light detection and footpaths in order to follow the traffic rules. Perception includes three sub-processes. Those are object detection, semantic segmentation, and object tracking. Now let us see about them. Now let us see about object detection. It is done to localize the objects of certain classes in a particular scene. Now let us discuss about the various algorithms for this purpose. We can't use classification algorithms for this purpose, as here there would be many objects and would be could contain numerous classes. So using a classical classification algorithms doesn't work, and we cannot use CNN also in this object detection. If we use classical CNN, it will apply classification on each and every pixel of the scene, and it produces various classifications, and the more accurate and confident ones are displayed with bounding boxes. But this is a brute force kind of approach, and it takes so much of time. Now let us see about the frequently used algorithm, that is reason-based convolutional networks. Let us see how the RCNN works. It basically starts with generating reason proposals using selective search by grouping the windows based on texture, color, and intensity before feeding them to the CNN network. And after generating this reason proposal, we will feed them to the pre-trained convolutional networks and extract features. Now we use SVM algorithm to classify the features, and next we use linear regression to get tight coordinates of the bounding box. There are also the fast working algorithms than RCNN, like fast RCNN, faster RCNN, and YOLO. Moving to the next, we have semantic segmentation. In semantic segmentation, each and every pixel is assigned to a class. This helps in uh, getting the drivable areas and separating the drivable areas from the obstacles like pedestrians, cars, trees, footpaths. Now let us see about object tracking. In order to drive safely in the real world, only object detecting doesn't work. We have to track the other vehicles and the obstacles in the real world in order to make our car aware of other cars' future trajectories. There are two prominent algorithms used in this object tracking process. They are SLAM and DATMO. SLAM is basically assumes the scene as a static environment, but when SLAM and DATO combination is used for object tracking, it gives much better results. Now let us discuss about the another crucial process of working of autonomous cars, that is planning. Planning is a process of making decisions in order to achieve the goal without compromising about the safety, and it is a process which begins with the current state of the agent or car and generates all possible states by performing legit actions in order to figure out a safe, optimal, and feasible path. We also get feedback from the control systems in order to keep up the planning to get the safest ride. There are three main methods in planning. They are route planning, behavior planning, and motion planning. Now, Aman will continue from here.
I am Aman Kumar and I will explain with the route planning. So route planning is done on a directed graph with the start and end vertices which represent the starting and destination locations, and the directed edges represent the paths between the vertices. This is a similar to weighted graph problem which where we can use graph search algorithm for finding the minimum cost paths. Most of the commonly used algorithms are A star, Rishetra and bidirectional search. Behavior planning. This is responsible for decision making that ensures whether the vehicle will follow the road rules and could interact with other agents in a conventional, safe, and without creating problem to the surroundings. It also ensures that the surrounding does not get damages with the action taken by the self-driving car. The behavior planning uses the route plan and produces a high-level behavior for the vehicle to know. Frequently used models are deterministic and probabilistic models. Motion planning. So it is a deciding on the sequence of action needed to reach a specific goal without colliding with the obstacles. Motion planners are evaluated on basically two criteria: the runtime and how well they scales with the high dimensional data. And the second is on the basis of their completeness. The planner is considered complete if it always terminates in finite time and always returns a solution when exists. If no solution exists, it indicates that there are no solutions. The search space for motion planning is very large and it leads to the high computational planning power. It also may require an exhaustive search of all the possible paths to guarantee the completeness. Cybersecurity and why we need to consider it in our self-driving vehicle. These are the potential attack gateways that a hacker or attacker could put threat upon while attacking on it. These are electrical control units, airbags, advanced driving assistance systems, engine steerings and brakes, onboard diagnostics, diagnostic port, dedicated short range communication based receiver, USB ports, passive keyless entry or remote key, remote link type app, and tire pressure monitoring system. These are the vulnerable attack gateways where an attacker could attack and poses threat to the self-driving vehicle. These are some of the important key attacks gateways that we have previously discussed in our slides. Some of the important attack gateways are electrical control units. These are the embedded system that controls one or more electrical systems within a vehicle and are connected via an internal network. They control systems and the risk arises when access to ECUs are breached and malicious attackers are able to access certain ECUs and the whole network. The next is OBD to diagnostic port. OBD to installed has been made mandatory after 1996 in the United States of America. These ports were originally mandated to permit monitoring of emissions. It's increasingly used to facilitate non-diagnostic features like enabling Wi-Fi and also enabling an insurance company to track usage through attachment of a dongle to the port. The third is DSRC-based receivers. It's being promoted as a means of encouraging V2V and vehicle-to-vehicle infrastructure communication. The short-wave communication can be subjected to spoofing and other attacks. Some of the common security vulnerabilities are as follows. Software glitches. Since the connected vehicle today contains more than 100 million lines of code, so it is obvious that the code could contain opportunity for bugs and mistakes. The second point is no single source of knowledge of or control over source code. Software for different components of connected vehicle is being written by different developers and installed by different suppliers, and no one source has knowledge of or control over the source code. Increased usage of app leaves vulnerabilities. Consumers are using an increased number of smartphone apps to interface with their connected cars and help run certain functions. Researchers have already demonstrated weakness in some of these apps. Need for constant update may be overlooked. With the increased use of connected features comes an increased need for continuous updates. And since due to low updates, it could provide harm and risk to the automated vehicle. These are the key cybersecurity takeaways that we could consider while making the automated driving vehicle. So we should provide with a multi-layered protection. We should also provide it and defend against externally facing potential gateways. We should ensure vendors and suppliers have strong securities, and we should promote timely updates so that the vehicle could be updated and not be vulnerable to the attackers. Data privacy and its concerns while making a self-automated car. Privacy concerns that is connected with the automated car. GPS monitoring generates a precious comprehensive record of a person's public movement that reflects a wealth of detail about her family, political, professional, religious, and sexual associations. While considering the existence of a reasonable social expectation of a privacy in the sum of one's public movements, it may be necessary to reconsider the premise that an individual has no reasonable expectation of privacy information voluntarily disclosed to the third parties. This approach is ill-suited to the digital age in which people reveal a great deal of information about themselves to third parties in the course of carrying on ordinary tasks. Some of the data privacy vulnerabilities that could be considered while thinking of a self-automated car are such as follows. The data that are related to vehicle journeys is important and should not be disclosed with anyone. Data on consumer habits and preferences. It could be used by companies for making personalized ads and if it is accessed by the other companies. Data from or related to children's and differences regulation between the markets. Some of the key privacy takeaways that could we take from the data privacies are: it should be built privacy protection into system design. Collection of some form or any form of consumer information would be taken only after the consent of the customer. Recognizes that children poses special risk. Limit collection of sensitive information and plan for and be ready to notify consumers in the event of an incident. The conclusion that we could draw from this presentations are as follows. The physical handlers of a car like brake, accelerometer, steering are controlled based on the output of a perception and planning process to reach the next stage by following the safe and legit actions. Controllers also passes the feedback to the planner about the next configuration for error minimization. Vehicles later found to contain defects and cybersecurity vulnerabilities could possibly dangerous for human life. Breach of vehicle system that store consumer data and the subsequent release of sensitive information may affect the privacy of an individual. These are the following references that we have considered while making this PowerPoint presentation. Thank you.